Yeah, so hey everyone, we will be doing the final workshop of our series on graph attention networks today, and this is uh, this is our GitHub page uh, or our repo which contains all the notebooks and YouTube recordings, and we have posted the notebooks and recordings till the last workshop. And once the recording is done for this, we'll also post that. So for today's workshop,
Can
uh,
can you increase the font a little bit,
okay,
please?
okay, here.
Yeah, yeah, and especially show the link to the repo.
Yes, it's here. This one.
It was down there also.
This one. Yes,
Yeah,
yeah.
yeah.
Repo
Okay,
link is here. This one is our repo link.
okay.
So to access the older notebooks, you just go onto this link, github.com UA-data lab graph ML. And for today's workshop, you just have to go click on this collab notebook here. So once you click and open a new tab, it should open, and yeah, this is the collab notebook for today's tutorial, which where today we'll be focusing on graph attention networks. And once you click on this open in collab link, it should open in collab. Okay, and before we start our discussion on graph attention networks, I want you to go to runtime here. I can maybe zoom in and show. Okay, go to runtime, go to change runtime type, and if you have CPU selected, change it to T4 GPU. Since I already selected T4 GPU here, so it's selected now. So you can just go and save. Yeah, and then click here on connect. So once it's connected, it will just show that okay, your GPU is connected. Yeah, so it will say okay, like you are connected to a T4 runtime with some allocations for your compute, like some RAM, some GPU, and some disk space available. And it also tells you that for how much it will run. So it's more than enough for us. This workshop is only like 55 minutes. It will last up to 2 hours. So okay, so let's get started with the graph attention network. So before we even start graph attention networks, we'd like to go back to our previous tutorial on graph convolutional networks and see that how graph attention networks build on top of graph convolution networks to produce even richer embeddings and perform better on several tasks. So in graph convolution networks, we saw that we are using the degree as a normalizing function to normalize the node connections. And on the contrary, graph attention network, how they work is that they use dynamic weighting factors, which you can say like attention scores based on the embeddings for each node. And this concept of attention was introduced in uh, long back, I guess 2016, in the natural language processing models, let's say BERT and GPT-3. So and then this paper by Peter in 2017 introduced the attention mechanism to graphs, and they found that it works better than graph convolution networks. So before we go to graph attention networks, we first have to understand what is a graph attention layer, how to build a graph attention layer using NumPy, and then we go to build a graph attention network with PyTorch geometric. Okay, so to understand graph attention networks, we need to first understand that all graph neural networks integrate node features, but the mechanism of the way they integrate node features is different. Since like in tutorial 3 we looked at vanilla graph neural networks where we just multiply the adjacency matrix with the node features to tell the model that there is some graph connectivity. Next, we in graph convolution we divided those features or the adjacency matrix by degree matrix to normalize the contribution of each node. We don't want to have a scenario that a node which having more connections is just dominating in the learning. So that's why we normalize with the degree. And here we extend it to this approach that based on the node embeddings or the node features or node vectors, those node vectors can change themselves based on the connections they are making with different nodes. And that's the whole concept behind attention, that nodes should have this flexibility, that they should be able to weigh their connections differently based on the connectivity, or based on what other based on what vectors or embeddings other nodes have. So, so to compare graph convolution with graph attention layer, first we need to see like why graph convolution is limited, and then how we can build on top of it. So from tutorial 4, we can see that graph convolution networks, uh, it's we have so it's like since we are normalizing by the degree distribution, the significance of nodes with fewer neighbors is amplified, because we are now uh, putting less emphasis on nodes with a lot of connections, and it, in a way, trying to normalize the effect of degree in graph convolution networks. Yeah, same way, how graph attention works is that it introduces weighing factors based on the context or specific features of the nodes, and these are referred to as attention scores. And this operation is similar to the attention operation in natural language processing, that you try to change the vector embeddings of each word based on the context in which those words appear. And same thing is similar thing goes for the nodes, that their embeddings change based on how it's connected to other nodes. Yeah, and some of the key components of a graph attention layer is that once you define the attention coefficients, you have to do a linear transformation, that you take the scores from both nodes and then calculate uh, some kind of compute hidden vectors for all the nodes, and then that becomes your attention score, that you define some attention weight matrix here, which you multiply with all the node features, so that based on those weights, you change the embeddings once you multiply the original embeddings via this learned weight matrix. And yeah, next is your activation function, which is a standard for all the neural networks that you have, let's say, sigmoid or tan inverse. So right now we have activation functions such as this rectified linear unit, and then you have modern versions of this rectified linear unit, which is called leaky ReLU, which has a small slope for negative values, and the functions looks like this. So for negative values, it has a lesser some slope. It's not zero, but like a very small slope. and and then since then we have softmax normalization, because once you have this attention score calculated, you want to normalize them to the same scale, so that some of, let's say, the raw attention score, no, not one single node dominates uh, compared to others. So that's why we normalize them column wise, and then they becomes normalized attention scores. And then comes multi-head attention. This mechanism was introduced in the attention paper. That Yeah, so the authors of the original attention paper claim that attention is not very standard. It's like keep changing or just fluctuates a lot. So what you do is put multiple attention layers one after the other, and they found that this helps the learning, uh, and enhances model stability. Okay, and then to do this process of multi attention, they introduced two methods, like either you can average those or can concatenate those results. So in the first step, when you have multiple heads, you can average those heads to get a average attention score for all inputs. Or alternatively, what you can do is, since you have multiple heads, you can concatenate them together. And usually concatenation is done so that it preserves the distinct information learned in different attention heads. And in matrix form, what we can see is that once you have this feature vector, you have this learned matrix W, then you have this attention scores I of j between nodes ij, which tells us that this is, you can think of as like an importance score or an attribution score between different nodes. And similarly, in a graph attention in the graph layer form, you can think of as this A tilde as your adjacency matrix, X is your feature matrix, and if you remove this WA, this just becomes your standard graph convolutional network once you normalize by degree. And this is your learned feature matrix, this W. So now we can look at uh, yeah, now we can look at the implementation of this graph attention in NumPy. Okay, run. Okay, and this example is the same as previous tutorial, that we have this matrix A, and we are starting from this matrix, which, so originally in tutorial 4, this matrix didn't have self loops, but right now we are starting with a matrix, or an adjacency matrix, or a graph with 4 nodes which has self loops inside. So how these self loops are made, that for all the diagonals you just add an identity matrix to the original adjacency matrix, and once you plot it, you can see that, yeah, once the figures, then you can see there's like self loops for each node. And this is done to tell the node about itself, that okay, you have to focus on yourself also, and as well as your connections. And then we can generate a feature vector. Since this is not related to any problem, there are no features, so for each node we can generate some set of features from a random uniform distribution between -1 and 1. Okay, and now since we have this feature matrix each, so this feature vector belongs to node 0, then you have in row number 2, you have this feature vector belongs to node 1. And so these are raw feature vectors, and based on the learning, we'll see how these feature vectors change. And then moving forward, we need two things. The first one is the weight matrix for these features. And this is the standard weight matrix for any kind of neural network. And the next would be your attention weight matrix. And this attention weight matrix will have these learned attention scores. And an alternative way is that usually what people do is use the Xavier and He initialization, but for this tutorial, we'll just initialize them using our random uniform function. Yeah, and now we have this weight matrix of size 2 comma 4, and then you have the same attention matrix of 1 comma 4. Okay, and now we need to know that which nodes are connected to each other from source and source to target. So what you can do is we can see that wherever and this we can, and for this purpose, we can use the adjacency matrix, that wherever the adjacency matrix has a value of greater than 0, we'll think, okay, then there is exist one connection. So let's say we go back here to our plot of this network and see how many edges are there. So there's like one edge between 0 and 1, 0 and 2, node 0 and 3, and between 2 and 3. So for these 4 nodes, we have total 8 edges. So 4 of these edges are between different nodes, and there are 4 self loops or self edges for each node. And then we can go and verify here that there are connections. And since this is not a directed graph, so you'll find that okay, there are like edge exists between, let's say, node 0 and 1. So that same edge can be thought of as an edge existing between node 1 and 0. And so that's why we have these many, I think, how much, yeah, 12 edges. Okay, and now we can do this matrix multiplication to concatenate all the hidden vectors for the source and destination nodes. Uh, and now we go back and look at the attention operation, which was defined here. This one, this. A of ij. This is the concatenation operation, and now we'll multiply it by the attention matrix here to get the attention scores. Okay, here, and now we multiplied the concatenated feature matrix with the attention matrix here. So now we have this A matrix here. Now we can go and plot it, or just display that how A looks like. It's taking a lot of time. What's happening? Yeah, and then you can also see like what's the shape of A. Yeah, since because we have 12 edges, so each edge will have like one score associated with it. That would be like the, you can say like the importance score for each node, or importance score between two nodes, and that edge would contain the score, so that becomes your edge weight based on the attention. Now we can pass this through the activation function, which is leaky recurrent linear unit, and we apply this function apply this function leaky recurrent unit to matrix A, and then it converts to this matrix E, which has this the output of the function of the activation function. And once we check the shape, it matches with the original shape of matrix A. And now the issue is that this matrix should resemble your adjacency matrix, because uh, unnormal so these scores are unnormalized, and since some nodes are not connected, so then those scores should be zero, because for example in the graph node 1 and 2 and 1 and 3 are not connected, so for them the scores in the adjacency matrix should be zero. So what we do is try to organize this matrix E, which is the output of the activation function, and we organize it into a nice form which has and then we convert it to 4 by 4, since we have 4 nodes and some of the edges, and we can see that okay, since there was no edge between node 1 and 2 and node 1 and 3, we have these two values as 0. And similarly goes for, let's say, node 2 and 1 and 3 and 1, because our graph is undirected. And now what we can do is use a softmax function to normalize our final attention coefficients here. Okay, yeah, so now finally we got the attention coefficients uh, for our graph. And then what we can do is utilize this matrix to compute the resulting embedding layer for each node. So this function comes from the above formulation for the graph attention layer here. And yes, and then we print the matrix H. So this is our attention operation, and then we first defined some feature vectors for each node, and then we use the relative context of each node corresponding to the other nodes to which it is connected, and then we have this matrix H for each node. Yeah, and then so this is just like one self-attention based implementation in NumPy, and to incorporate multiple attention, we can just replicate this process over and over to have different weights and attention mechanisms, and then concatenate them together to have multi-head attention. Yeah, now we can look at GAT, this graph attention network in PyTorch. So we'll use the torch geometric library to get the graph layers, and we'll use the same datasets as we were using in tutorial 3 and 4. So we have like three right now. So here I am using 3 datasets, uh, Quora, Facebook page to page, and there is like 2 more datasets, sites here. So these 3 are for classification, and then we'll use 1 more dataset for regression at the last. So let's get started with the Quora dataset here. Okay, you can set the seed and then then import this GAT version 2 convolution layer from dot geometric. You can define the accuracy function, and this is the standard training module you write in PyTorch, where you define the graph layer first here in the initialization function, and then say that, okay, how many heads you want to use. So right now this is using 8 heads in this layer, and then one single head in this second graph layer. Then we have this dropout, and then the activation function, then dropout again. Then, and since we have 4 different classes in this for this example, then that's why we are using log softmax. Yeah, this implementation is very standard and same as the vanilla graph neural network and GCN from previous 2 tutorials. Okay, and once we have this data set, we can train this GAT. Uh, yeah, one thing which is important to mention here is that although this model is running, it's not running on the GPU, because we haven't pushed anything to the GPU, because in PyTorch you need to push the model and the data to GPU before training. So yeah, since these are like small examples, we don't really need to use GPU here. But once we go to the regression task where we have a very big network, there using GPU is beneficial. And here we see that the GAT accuracy is about 83.3%. Same thing we can do for Facebook page-to-page dataset. Yeah, again, it's a very small dataset, so training would be easy. So let's say how much time this takes. Yeah, while it's training, do you have any questions, Carlos?
No, everything's fine.
Okay. Yeah, we can wait for it to train. Let's say it should take like 3 minutes to train. Yeah, one way to check if GPU is being used is not is like you can just go here and see the status. It will show you, okay, GPU RAM, you are not using the GPU RAM right now, but everything is running on system RAM and CPU. Yeah, I guess probably should have started the GPU first. Yeah, just takes a lot of time. Okay. Yeah, from here on should be easy, I think.
How many epochs are you training?
100.
100. Okay.
Yeah. Yeah, sometimes like I think this is the one data set, Facebook page-to-page, it's take a lot of time to train.
Mhm.
Yeah, ideally I should have put it on GPU and just train like 10 seconds.
Okay.
Yeah. Let's say two more minutes. because other than this, I think other models are easy. So I think we don't need Planet's PubMed today. Yeah, I think for this, it's like after 60 epochs, it's the same. There's not huge difference. Yeah, but it just takes a lot of time to train, maybe like 10 minutes now. Yeah, I think based on my experience, GAT is like marginally better for most of the cases. So it's not like it will give you like a
Mm.
huge advantage for most of the problems, at least based on the models which I have ran before.
So in this case, 50 epochs was enough because
Yeah, I
that's
think so.
converging
50 was enough. Yeah,
and the learning rate.
yeah. Ideally, it's like this, like a standard learning rate. I'm not like decreasing by epochs. I don't know where I mentioned, but here somewhere, right? Yeah, here 0.01. So yeah, ideally, what I do is like probably decrease the learning rate as it trains. And it's like there's not like a big difference between like 0.34 and 0.331 from let's say epoch 60 to 80. So yeah, last 20 epochs, and yeah, this should be done in like 2 minutes. Yeah. Yeah, come on, last 20 epochs, come on. It ran for like 7, 8 minutes. That's like too much, I guess. Yep, it trained. Yeah, and then we are getting 91.45% GAT test accuracy on Facebook page-to-page dataset. Can now look at the other dataset from tutorial 3, which is the site C again, a citation graph. Yeah, let's see how much time it takes to train. Yeah, this is faster. Okay, so the GAT network is trained on site C, and now we can test it. How much it gives? It gives us 69.2% accuracy. So now it's like different from run to run. So let's say we can update the values. So uh, for the Cora dataset, we got 83.3. For Facebook page to page, we got 91.45, and for site C we got 69. So 80.3, 90.4, and then we got 69.20. So marginally better than my previous run. Yeah, so these values come from tutorial 3 and 4. So in tutorial 3 we looked at MLP and vanilla GNN. In tutorial 4 we looked at graph convolution network, and this is our current tutorial where we're looking at GAT, the graph attention network. And this is the comparison that for some problems, like let's say Cora, it performs really well, like almost like 5% increase, 4 to 5% increase in the accuracy. But for let's say Facebook page to page or site CA, we don't really get a lot of improvement. It's just like maybe 1 point or 2 point improvement here, like a very small. Yeah, now after these classification problems, we can look at node regression and see if GAT can work in node regression or can outperform GCN on regression task. Yeah, and this data set is big, and this graph is big, so that's why we will put it on GPU to training. So once we extract the data from data set, we can check the GPU, and if available, we can set the device to GPU or to CUDA so that we can use the GPU. Now we put the data to GPU, and this is just like a way to say that, okay, how many nodes are there, how many features are there, how many classes are there, and then if there's like loops and edges, directed edges are there, or the graph has loops. And more information about this dataset is available in tutorial 4. I can just mention here that originally this graph is for regression, but they converted it for classification by binning the regression values. But we are using the original regression values from this zip file from this website to do the regression problem. And these values are nothing but just the log transformed page visits, because there's like a huge difference in the minimum and maximum. So we're trying to log normalize them to make them more easy to train. Okay, now we can check what data we have. We are now using CUDA as our device. This tells us that we are training on GPU now. Okay, we move the labels to the device. Okay, now we are trying to just change the format of the data so that it matches our model. And now we'll include these two metrics from sklearn library, the mean squared error and mean absolute error, just to compare this with different models, the GCN and MLP. And the GAT model remains same as the classification. The only change here is that we are using a 3-layered network here, and there is a difference in loss function, that instead of cross entropy in classification, we are using the mean squared loss error. That's the one change. And the for metric, instead of accuracy, we are having the train loss and validation loss here. And once we have these losses, we can print out or evaluate all the three metrics, let's say mean absolute error or squared error, or some other metrics of regression. So once we can check this, we can put this data and define our GAT. Okay, GAT reg is not defined. I think I forgot to run this. Yeah, now it should be good. Okay, yeah, so in the previous steps, we moved our data from our CPU to GPU. Now it's time to move our model as well. So it's very simple. You just have to do like model name dot to and put the device here so that the model moves to GPU, and can check the data and then try to fit. And then this would be like very quick. We are training for more epochs, but this would be quicker because we are training on GPU now. And you can go and also look at see how much GPU RAM we are using. So we're just using like 1.5 gigs of RAM. Instead it was 0 before for other tasks, but now we are training on GPU, so it's trained now. And okay, you can look at the GAT test loss, which is about 5.53. Now what we can do is we just had a loss now, but we need to calculate other metrics as well. Let's say the mean squared error, root mean squared error, and the absolute error. So for that, we'll get the all of the output from the model, put the output to CPU, and then then calculate the predicted values for the test set, because this works on all of the data set, but since we have a test set, so we are using this test mask function here to just get the predictions for test set, and then we can calculate the mean squared error and mean absolute error based on the original regression values for the test set. Once we calculate this, we can print them out. So what we found is that for this network, the MAE is 0.5660, RMSE is 0.73, and MSE is 0.5337. And once we compare this, I can zoom in. So to show that we have GAT compared with GCN and MLP, and GAT outperforms these two models on all three metrics. For example, MLP is our baseline, like for any model we first train the multi-layer perceptron transfer to set up a baseline. So that was like way above 1, and the absolute error were also high, and all these metrics for regression are lower. The lower they are, the better they are. And for GCN, we have 0.59, which is lesser than the metrics or the MSC for MLP, but for GAT we got 0.5, which is even more lesser than MLP and relatively lesser than GCN. So this proves that GAT is an advanced model, and it builds upon the graph convolution model to provide us a better way to model our graphs. Yep. Yeah, thank you for joining.